So as I was saying, the first year, the programming language of application teams have been focusing on neural networks, although actually it turns out that a lot of our work is actually fairly agnostic to what sort of machine learning system you have, because we're working on the infrastructure that really sits on top of these systems. So let's suppose that this box contains all the problems in the world, and these are the problems that are solvable by neural networks. So the question is, what sort of properties are we interested in verifying? So you have another set of problems, which are those problems that are solvable by, classic algorithms, non-machine learning algorithms. And these are the ones that, that we have spent the last 40, 50 years trying to learn how to verify. And if you're in this intersection and you're trying to solve one of those problems using a neural network, well, then you have some really nice properties, because you can just say, I want it to have the same behavior as a classic algorithm. The problem is that actually this intersection is very small. There's very few scenarios where you actually know how to solve it classically, but you're going to use a neural network to do it. Not zero, and I am going to discuss an example in the talk today, but it's small. The more interesting set of problems are those that we don't know how to solve using classic algorithms, but do know some of the properties of desired solutions that we would like. If we could come up with a machine learning solution, we know properties of what that system should have. And those are the ones that we're really interested in trying to learn how to embed into our neural networks or other machine learning systems. So what sort of properties are we talking about? It's very easy to point out these abstractly. I'm going to go through some examples. As Lorenzo pointed out, I put exactly the same picture as in Lorenzo's slide. There's no machine learning, and so machine learning talk is complete without the panda picture. It's robustness. Your neural network or your machine learning system should be robust to small changes in the input. It should only produce small changes in the output. And there's lots of tags which cover. But there's other properties on it. And then you can define this mathematically, as Lorenzo did. Not defining it in quite the same way, but we're going to say our function is going to be a neural network F, and we're going to have some input in the training data set, which we know is correct. And we have some abstract notion of distance. And that's a really hard bit, actually, in my opinion, trying to come up with a good notion of distance, because you don't just want Euclidean norms or things like that. And in this formulation, you say that if you're, for every point that is no more than epsilon distance away from your training data point in your input space, then your output shifts by no more than delta. So you can formulate this property mathematically. However, there's other more interesting domain-specific properties that we might want to embed into our system. So let's consider a simple loan application system that we are trying to predict your score for your application ahead of time before you apply. So as inputs, you have your applicant's income, you have their credit score, marital status, etc., all the different things that you might want to, you think the decision might be based on. And as outputs, you're going to have your predicted application score. So what is a property that we might want a neural network that we were trying to get to learn this stuff to have? Well, you might want it to be, in fact, you almost certainly do want it to be monotonic with respect to the income input. So if you know for a fact that if you have two applicants and they're completely equal, then the applicant with the higher income is never going to have a worse score than the applicant with the lower income. Now, hopefully, your neural network might be able to learn this from a training data set, but it's not guaranteed. And you would really like to be, you might want to really make sure that your neural network has actually learned this fact. And that would be a really good indication that it is learning something useful and that it's actually coming up with the right answer. So you can again formulate this mathematically. You can say for every two inputs, X and Y, if the first input, i.e. the income is X, for that X is less than equal to income person Y, and all the other inputs are equal, then you want the output to be less than equal to, or X less than equal to Y. So that's an example of simple example of a monotonicity property you might want. And then you can have more complicated systems. So this is the ACAS Zoo system. It's a collision avoidance system for unmanned autonomous aircraft, which was developed about 4 or 5 years ago, I think in the States. And you are an autonomous drone flying about, and there are other drones flying about. And it'd be really nice if you didn't crash. Very expensive if you do. So they came up with this system where you have various inputs. You have the distance to the intruder. The intruder is the other drone. You have its angle to it. You have which direction it's going. You have your own speed. You have the intruder speed. And what you'd like your system to do is produce an output, and you can produce a score for 5 different outputs. You can produce a score for clear conflict, which means you're not going to crash. You don't have to do anything. You can say, I really think you should turn strongly left at this point if you're quite close. You have a weak left, weak right, and strong right. And this system is actually used in drone systems that are currently in production. So they originally implemented this system for predicting which action you can take using a 2 GB lookup table. But this was replaced with a neural network in order to improve size, so shrink it, and I think they also mentioned something about latency requirements. So they took this lookup table and they kind of extracted some properties that they would like the neural network to obey once it's been trained. And we're going to look at the 6th property because I think it's the most interpretable and easiest to understand. And it's basically, if the intruder is a long way away, then the network should advise clear conflict.
Just reminding everyone who joined afresh how to find Slido, because they wouldn't have history of this.
That's true. Okay, and we have this definition, and it's not super readable, but basically it says if they're not pointing in the same direction as you, and for instance, you see the mouse, if the distance, if you're over 12,000 feet away, it's in feet because it's US, of course, then you want to advise clear conflict. Cool. So there are, hopefully I've convinced you that there are properties that even in tasks that we use neural networks to solve, there are properties of interest that we want to embed in these things. So how would you actually go about embedding these things in your neural network? Well, you're going to formulate your property. That's actually one of the hardest parts. Glossing over that entirely in this talk. Let's suppose we have it. You really want to train your neural network. And actually, you can't just train it on the data set, because the data set may not be sufficient to learn that property. You really want the training to be influenced by the actual definition of property that you found. And there are various frameworks to do this. DL2, ACT, and they incorporate the property into the training. Once you've done the training, you don't want to move to verification straight away, because the problem is that verification is very expensive. It may take hours and hours and hours, days to verify your network. You want to do some lightweight attacks on it to try and find some counterexamples to your properties first, using things like gradient descent, or cheap methods of finding counterexamples. And again, you want the property to influence a counterexample search. And again, there's various techniques to do this: PGD, FGSM. I think we mentioned FGSM earlier. And when you find a counterexample, you may have to go back and do some more training. And finally, there's also, once you have exhausted all the counterexamples you can find easily, you move on to verification. And again, in the last 4 or 5 years, there's been a lot of tools come out that actually which can take neural networks of up to 1,000, 10,000 nodes, even 100,000 nodes if your properties are simple enough, and can take a neural network and say, true, yes, this neural network satisfies this property, or no, it doesn't. And again, it may come up with counterexamples, in which case you're back to square one, you're back to training. Or it might shout success, you proved it. Okay, so that's great. Let's now take a look at some of these tools and how you might go around using these tools to embed. So this is a training framework called DL2 that I mentioned earlier, and this is actually embedding the robustness property that I talked about earlier. Now, does anyone from the audience, either online or anyone, have any comments on this as a implementation of robustness property? Any first impressions that jump out at you?
Why is there a comment about that?
Why is it comment about that? I took a screenshot of GitHub of this is actually their code on GitHub. So I'm not claiming that I'm writing this myself.
It's a bit harder to read than your mathematical definition.
It is so hard to read compared to mathematical definition. If you were okay, domain expert, this isn't a property that you have domain experts in. But as someone coming in, it's super difficult to tell that this is actually encoding the property that we were talking about. And actually, it's also very tightly coupled. If you know some Python, it's actually very tightly coupled to PyTorch framework. So it's not portable between frameworks. So it really suffers on the interpretability front. And yeah, that's property. This is another training framework. This isn't the robustness one. This is the AISEC property. Trying to introduce far away, clear of conflict. So this is a little bit more readable. You notice it's a completely different set of code. It's not a common interface. It's a little bit more readable in the sense that you can actually see which variables are related to which. But again, unless you know exactly what these variables mean and exactly what you're doing, it's not, you can't look at it and go, yes, that is a property I wanted to encode. And also it achieves this readability by in fact only being applicable to a very limited subset of properties, and it actually just bounds your inputs, bounds on your inputs and bounds on your outputs. So this is a verification framework called Marabou, and again this is the AISEC property. This is even less readable. This is just a set of numbers, but again, different input format. It's not portable to the others. Eran, another verification framework. This is even worse, right? What does this mean? This is actually their code that they write their verification conditions in. And it's just completely meaningless. There's no relationship to variables or anything. This is just what people write. Super clever tools, by the way, incredible stuff going on underneath the hood, but really not, not usable, not interpretable, not what you want to build your systems on top of. There has been some push to try and standardize these input formats. BNNlib is a format which is basically a souped up version of SMTlib for writing SMT constraints. Okay, it's standardized, but it only really applies to verification frameworks. And it's still not that readable. So there's actually other problems as well with these. We've talked about this life cycle, but success isn't really the end of the story, right? Once you verify your neural network, because you're not really interested in the fact that your neural network, the end goal is not with the neural network based property. The idea is that you don't care about whether this neural network advises clear of conflict for if the intruder is far away. What you care about is that these systems are not going to crash. The autonomous fluents are not going to crash when they're running these systems. So actually, you're interested in the property of a much larger system that incorporates a neural network. And this is what we think that all this work that has been done on these different stages of the life cycle is really missing. There has been very little work on how you actually integrate these properties of neural networks into tools that will allow you to prove properties of a larger system as a whole. So to recap, the problems are interoperability. It's super difficult to port properties between different stages of the life cycle. Interpretability, you can't take a domain expert who's not technical, in the sense doesn't know about verification, but they can't look at your property in your verification framework and go, yes, that's the right property. And integration, you can't actually link these properties to larger properties about larger systems. So what is our proposed solution that we come up with? Our proposed solution is something called Vehicle, which name possibly subject to change later on, which is a domain-specific functional language for writing high-level property specifications. In our case, initially for neural networks, but maybe branching out to wider systems. And the idea is that you will be able to write the property once in this high-level language vehicle, and then it will automatically be able to generate appropriate code for each of these tools at the different stages of the life cycle. So we're stressing we're not coming up with our own algorithms or to solve these problems, but this is purely an interface that can be used to integrate all these steps of the life cycle. And most importantly, on the right-hand side, once you have verified your property, you'll then be able to export your property into code, into interactive theory improving systems like Agda or Imandra that Remy is going to talk about tomorrow, or for instance, Kimara, which is a proof system for reasoning about differential equations in control systems of cars or things like that. And it will actually integrate, so you'll be able to write code in those systems against the property that you put in vehicle. And we also hope it's actually quite difficult because to actually plug all these systems together, and it's very easy to write properties that are amenable to training or verification, but they often don't. Ways of writing these means that if you come up with certain ways of writing these, it often means they can only be used in certain steps of the pipeline. So we think that actually we can really help with usability of these tools as well by doing some analysis of the property and trying to help the user to get their property into a form that's actually amenable to all steps of the pipeline. So at this point, it'd be great if I had a working demo. We're not there yet, but we're still working on the type, implementation of the type system and the compilation down to these different tools. But I'm going to give you a flavor of the code that we're hoping to write. So we're going to go through the APAS Zoo example. Apologies, I'm suddenly aware that maybe these color scheme isn't the best. I'll try and maybe that'd be great. Is it unbelievably difficult to read?
It's fine on Zoom.
It's fine on Zoom. Okay. Well, if push comes to shove, everyone. Cool. Okay. So you can have named meaningful constants. Like in the APAS Zoo property, it references 3.141, but really that's pi. So we're interested in that. You can have type definitions. You type definitions just like any most functional languages, and you have keywords for network declarations. So you can declare a network with a certain type, but you don't have to provide an implementation. So you just say, I have some network that has these inputs and these outputs, but I don't care what it is. You can then have local function definitions like this. So these are simply taking an input vector and extracting the various components of it, so that we can have more readable code. Similarly for outputs, so this is a function that takes an input vector, applies the network that we previously declared, APAS Zoo, applies it to it, and projects the first output, which is a clear complex sort. And once you've written this boilerplate that you hope you're able to extract over all the different properties that you wrote for this network, you can actually come up with a property that is actually readable, or we hope a lot more readable than the other frameworks that we've shown earlier. So you can actually define what it means that the intruder is far away, and an domain expert can look at that and go, yeah, that actually makes sense. What it means to advise clear conflict, and the actual final property that says for every input vector x, if the intruder is far away, then the system advises clear conflict. And you'll be able to write this code once, and it will compile down to various different tools, or give you warnings about why it can't, like meaningful warnings about why it can't, why this property is not suitable for various tools. And it's, yeah, simple. As I said, we're still in the middle of implementation. Wayne is hopefully going to talk a little bit more detail about what the internals of the vehicle and some of the design decisions we're making. Very briefly, we have various planned language features, module systems, built-in language support for talking about training data sets, and enumeration types loaded from files inspired by a lot of networks that are used in natural language processing. They often talk about vocabularies. You really don't want to have to specify your vocabulary in vehicle, so you should be able to just load in a file and start talking about instances of vocabulary super easily. Feedback is super welcome. Lorenzo's talk was particularly present. I mean, there is this whole problem of non-invertibility from, you're writing your problem you're writing your property in the problem domain, and somehow you've got to map it to the feature domain. And yes, this is an open problem of how to solve it, but we're hoping that this is a big step forward. This will be a big step forward in actually usability of these systems and actually allowing people to build bigger systems on top of them. Cool. But yeah, thank you very much. Yeah, looking forward to some questions after.